Hey students, I wanted to make a little video here of some examples. I ran out of time in class. We did a good job of going over chapter 15. Maybe I should put here, chapter 15. But just ran shy of showing you some examples, although I did a bunch of examples from the homework. So that's probably the best thing I can say. But I thought that maybe these would be helpful. I kind of skimmed through the book and found 5 good examples that I thought would be useful. So I go, hey, let me kind of give these a try here. So starting here with number 4, let me go ahead and I printed it out of the book here. It says a hanging spring stretches 35 centimeters when an object of mass 450 grams is hung on it from rest. Now, let me pause right there and make myself a little picture. But if here's the spring kind of by itself with nothing hanging on it, then when I add, and it's 450 grams, but I'm going to convert that into kilograms. And so when I have 0.45 kilograms hanging on it, it stretches some extra distance, which they tell us is 35 centimeters. So I'll write it as 0.35 meters. And so if we apply Hooke's law here, and maybe even just the absolute value, let's not worry about the negative. The force stretching the spring is the weight we're hanging from it, mg. And then, of course, the force from the spring pulling it back up. So this is the down and this is the up. They're equal in magnitude to each other. And that'll give me a chance to find the spring constant. It would be mg divided by how much it stretched. And so we've got 0.45 kilograms. We've got g at 9.8, and we've got it stretched 35 centimeters here. So grabbing my calculator here, 0.45 times 9.8 divided by 0.35 gives me a spring constant of about 12.6. And then the units are newtons per meter. So that's the first piece of information I get when they tell me that in this situation, or excuse me, when they hang this much mass and it stretches this far. So as I go on to read, it says, in this situation, let's define x equals to be 0. All right, so as it stretches down, we're going to call this the 0 mark. Okay. The object is then pulled an additional 18 centimeters and released from rest, and it oscillates without friction. Okay, so I guess in my picture here, and maybe continuing on with my picture, so here's the x equals to 0. Now we've stretched it even more, 18 centimeters more. And then we release it. And so this thing's going to go up and down and up and down. And so a graph of its position, and it's a vertical position, even though I'll call it an x here, versus time, would then, according to this, start as a negative value of 0.18 meters, and then go back to equilibrium, and then go up, in this case, to a plus 0.8 above that equilibrium, and then continue to oscillate. And so the whole point of this chapter was that many things oscillate, and the simplest one to talk about is the spring. And so a spring in a mass, and even though it's a vertical spring, as long as we readjust what they call 0, that where it hangs at equilibrium, and so that's what they're doing in this problem, we learned that it had that same basic equation as any oscillation. that it goes up and down, so it's either a sine or a cosine, depending on how you initiate it, and so that kind of determines the value of phi. Probably this one is easy just to look at visually and say, well, this is going to be a minus cosine function. Of course, I guess we could spend a little math and say, well, how do you turn a cosine function to look like a minus sign? You either add a pi or subtract a pi. So you could say phi equals pi. And so I guess this is the same as saying a cosine omega t plus pi. And also, because it repeats every 2 pi, it would be the same as a cosine minus a pi. But all of that probably is just making it harder because we have 2 variables in here. So I'll keep that in mind, but I think I'm going to probably want to be using this particular equation for this problem. I don't really know because I haven't asked me too many questions yet, but I think I'm getting there. And of course, let me take one more step. Since they told me I pulled it down 18, it starts down, so I'll put a negative 0.18 cosine omega t, where omega is the square root of k over m, which in my case, and so maybe I'll call this page 1. Okay. But coming over here to page 2, this omega, which is the square root of k over m, is going to give me that angular frequency. Let's see, what did we get for k? So we got, oh, and it's still in my calculator. So we got the 12.6, and so now I'll divide it by the mass. I believe that was 0.45, yeah. And then taking the square roots of that, we're looking at an angular frequency of a 5.291. I suppose, because I'm kind of looking ahead, they ask about oscillations in a period of time. I might ask for the period here. How much time does it take to go back and forth? And so let me go 2 pi divided by omega, and I get about a 1.187 seconds for, I guess this would be radians per second for angular speed. But here is the angular frequency. So finally, I can put this in here by saying, okay, so x equals negative 0.18 cosine, and my omega is 5.291 t. This would be the mathematical equation describing the position of this mass as it goes up and down. Okay. And that's going to lead me right to the first question, fortunately. It says, what is the position x at the moment of 84.4 seconds later? All right, so I'll get that by just saying, all right, let's put in 84.4 seconds. Now, since these are all in real numbers, which is radians, I better make sure my calculator is in radians, which it looks like it already was. Good. So I could put the 5.291 for the angular frequency, and then the time of 84.4 seconds gives me 446.56 radians. So I'll go cosine of that number. And then multiply that by a negative 0.18. And it looks like I get a 0.162 and negative meters. Now, I suppose if I wanted to understand this physical picture a little bit better, I could say, okay, it started down here, and then it went up, and then down, and then up, and then down. And it did this a bunch of times, and maybe I should ask how many times. But eventually, it finishes down here. And let's see if this is up and this is down. Let me call this the 0 mark. 0. It finishes somewhere around here. Negative 0.162. And I suppose it could have been there on its way up, like right here, or on its way down. And that's where I think the period can be useful, just to kind of get an understanding of this. In fact, getting a little diverted because they probably don't even ask this part of the question. But to see if I understand a little bit better, it might be nice to take the 84.4 seconds for the total time, and realizing that it takes 1.187 seconds for each oscillation. This should tell me, how many times does it oscillate. And it looks like I have a 71 and just a little bit more. So coming back here, this would tell me it's going up and then down. That's 1 time. Up and then down. That's 2 times. And it does that a total of 71 times and then a 1/10 of a cycle. So that must be still on its way up, because this up here would be a half a cycle. And so if it was here, it'd be something more than 0.5. And so I can kind of scratch that out. I won't draw all 71 ups and downs, but there would be 71 of them, and then just this little extra piece right there on its way up. So that kind of gives me a little bit of understanding of what happened in all of this. And that might help for some of these questions later on. But in either case, I think I answered this first one. What is the position at 84.4 seconds? And then B, what if we had a different spring that stretched it not 35, but 35.5 centimeters with an object O? So it stretched it a little further and a little less mass. So this would be a different spring with it must be, let's see, the spring constant must be a little lower because it stretched it further and it did it with less mass. But if we define this new position to be x equals to 0, the object is then pulled down an additional 18 centimeters and released. So what this one's trying to say is in part B, we've got a different spring constant. And going through the same logic, our spring constant is mg over x. So in this case, the m is 0.44, and the g is 9.8. Let's see, the distance is such, hey, no barking. Go away. And so if we divide by how far it's stretched, let's see, how far did it stretch? The 35.5 centimeters. we'll kind of get a different spring constant. So 0.44 times 9.8 divided by 35, 0.355. And hang on here. Let me close my door. The dog keeps barking there at my neighbor. Okay, there we go. So this would be 12.15. And so we got a little different value. Let's see. What did we have before? 12.6. Yeah, and so a little bit lower. And so that means my angular frequency, which is the square root of k over m, is also a little bit less. So this would be the 12 and divided by, and let me see, another object. Yeah, and did they leave this on here? Object is pulled down and released. Yeah, so the same object, the 0.44. And so we've changed the mass here to 0.44. And now taking the square root of all of that, we get a 5.25 radians per second. Or a period of, let's see, 2 pi over omega. And so 2 times pi divided by the 5.25, and we get about a 1 point, I'll call it 20, or maybe I should do an extra decimal, 1.19, let's go with 7. And the point being here that if I compare the time for this oscillation, it's just a little bit longer than the time for this oscillation. Not by much. And I think that's what the problem is getting at, that, again, this is going to go up and down, but at a slightly different rate. And so when it asks, where is this object? Find the position 84.4 seconds later. I guess my equation would look something like, okay, so let me go to page number 3. X equals, and so there's the negative because we pulled it down to let it go, and we pulled it down by 18 centimeters, so there's my amplitude. And so just like we did back here on page 1, where we had this equation, where we wrote it here on page 2, this would now be 5.25, a slightly different angular frequency with a slightly different period multiplied by a time of 84.4 seconds. And so we get a position of 5.25 times 84.4, and then we get cosine of that number. And, very interesting. Negative. Okay, watch this. Times a negative 0.18. And we get then a positive almost 1.8. It's 1.78. So reading the math here would tell me, okay, it started down here at negative. It went up, down, up, down, up, down, up, down. And after 84.4 seconds, it's now very close to the top, nearly at the top. We could probably say it is at the top due to rounding. We could even say, how many times did it do this? Well, let's take the 84.4 and divide it by that period of 1.197. And look at that. It went up and down 70.5, and I'll call it a 1 times. See, and notice the 1/2. So it went up, down, up, down, up, down, up, down. And then right here down, that was 70 times. And then it did another half. And then it did a half and a hair. And so it's just a hair below because it's, 0.51. Well, the point, I guess, that we're going to see here in the problem is that the other one that almost had exactly the same period, almost exactly the same frequency, went up and down 71 and a hair more. And so this is 70 and a half. The other one was going at a little higher frequency and went all the way down. And so what's interesting about this is if you had started these at the same time, they would, go something like this. They'd be, almost the same, but one's a little bit faster, and they'd be like this. The slower one's going to be at the top, and the faster one's going to be at the bottom. Even though there's not much difference to them at the beginning or even at their frequency, after a period of time, they're off by a lot, a whole half a cycle here. And I think that's why they wanted us to do part B, because when it says find the position, and then right here, C, why are the answers of part A and part B differ by such a large percentage when the data is so very similar? So they are almost the same period. They are almost the same weight. They are almost the same spring constant, but one is just a little ahead of the other. And after a number of oscillations, which in this case is about 70 to 71, one gets ahead of the other. And it makes it look very different. And if you're wanting to see that they are different, this is a good thing. You let it go for a long time, and it's easy to make a measurement that show, yeah, they're not exactly the same, and this one is a little bit bigger by that. Of course, if you want to get them exactly the same, and you want them to be same at a long period of time, like 84 seconds later, you can see how difficult this would be. So I think we're kind of answering that question. Why are the answers to A and B differ by such a large percentage when their data is very similar? Does this circumstance reveal a fundamental difficulty in calculating the future? Yeah, obviously then that two things that look like they're the same within just a small measurement. In fact, maybe they only differ by so small that you couldn't even measure that difference. You're going to say, well, later on they're going to be the same in the future, 84 seconds later, but they're not. They're very different. And so we refer to this as chaos theory in math, that, hey, they're not that different. And so if you're going to make a measurement within the next, 1 second, you can say they're the same. But if you go off into the future, and especially if you look at like planetary motion, you go for 1 billion years, they may be very different, which is why we predict our solar system is going to be orbiting very different in 1 billion years than it is now. And it's probably why it was very different 1 billion years ago than it was now. And it's nearly impossible to predict what it was because we would have to make measurements that are so incredibly accurate that they got to account for this small difference. And so that's what we refer to as chaos measurements, chaos theory. So don't confuse that with, randomness. But I could go down a long rabbit hole of the difference between statistical randomness versus chaos. Anyways, let's go on then to D. Find the distance traveled by the vibrating object in part A. Okay, well, fortunately, part part A, I guess I answered C in a bunch of words. Okay. Calculate the distance traveled. Now, remember we said it went up and down. I think it was 71. Where was it? Here. Yeah, on page 2. On page 2, we said it went up and down 71 times and a little bit more. And we drew this picture, 71 and a little bit more. Let's just talk about the 71. In fact, let's just talk about one oscillation. One oscillation would start at the bottom and go up to the top and then come back down. And if this is the 0 mark and it has an amplitude of 18 centimeters or 0.8 meters, if I take that 0.8 and multiply it by 4, this is how far it travels, 0.72 of a meter for one oscillation, because it goes, from here to 0, that's 18, and then up to the top, that's another 18, back to equilibrium, that's another 18, and then finally down to the bottom. So 0.72 meters is what it does for one oscillation. So if we go 0.72 times 71 oscillations, we're looking at about 51.12 meters after 71 oscillations. But as we calculated, it went 71 and a little bit more. And in fact, we have that position. That position is at a negative 0.162. And so from the bottom to this little part here, it'd be that difference. It'd be, an 18 minus a 16.2. So 0.18 minus 0.162 is how far up it went, 0.018. And so this last little piece upward, I guess that's actually 1.8 centimeters, because this is in meters, needs to be added for the final motion. So 71.12, add to it 0.018, and I guess I did not include another significant figure, so I'm just going to call that a 2. And so this would be 51.14. And so I'm just going to put another, basically 2 centimeters. That's almost 2 centimeters. So 51 meters, 0.14 is how far this thing travels in part A, which is 71 oscillations and a little bit. Whereas part B would be 70 oscillations, and then a half oscillation, and then a little bit more. But now that I say that out loud, I think they deliberately said only part A. Yeah, they did. Traveled vibration in part A. So we don't need to do part B. I guess the author was thinking you've done enough work already. And you got the point. So we don't have to do B. No, there it is. Find the distance traveled by the object in part B. Okay, and let's do that. Part B, we said it went how many times up and down? Oh, here it is on this page. 70 and a half and a little bit more. All right. So let me do the 0.72 times 70 oscillations. Okay. Then the 1/2 is just from the bottom up, so it'd be 18 and 18. So that's 0.36. And then the small little additional movement is this little part here where it, went up to 18 and then dropped down 0.002. So I think that's going to be even, smaller than we can fit in here. So I think would be safe just to say it was, at the top. So 0.72 times 70 of these. And then the half cycle is 0.36. And so this comes out to be 50.76. And I suppose if we add that, we'll put a 2 down here. We can debate whether that's a significant number or not. But again, not a surprise, a little bit less. By roughly a half cycle here. Because I bet if I add the extra half cycle, yeah, we're right there. Actually, half cycle and that little change. All right. Well, that was a good first example. And hopefully give you some insight. It was a little longer than I anticipated here, but hopefully there was some good learning there. Like I said, it would make a good example one to do in class. We just ran out of time. Let's try number 10 then. Okay, so number 10. I printed that one too here. Let me see if I can find it. Here it is. And so number 10 says that we have a 1 kilogram glider attached to a spring with a force constant of 25 newtons per meter. It oscillates in a horizontal frictionless air track. At time t equal to 0, the glider is released from rest at a negative. Okay. So in terms of left and right, it's over here, negative 3 centimeters. That is, the spring is compressed, so they have some kind of compressed spring here. And so it would go back and forth, back and forth, back and forth. And so I guess we could write that as x equals to a cosine omega t plus phi. This was our solution for the easy problem, which this is the easiest one, the horizontal spring on a frictionless surface, where omega is the square root of k over m, and the a and the phi are how you initiate it. And if you were to plot a graph where position is on the vertical axis and time is on the horizontal, it would start here and rock back and forth. So it would look like a negative cosine function again. In fact, we had this discussion already here on this first example, number 10, where we said you could write this in a lot of different ways. You could write it as a cosine function that's been shifted by either a plus pi or a minus pi. Or you can actually do the trig identity of two angles and come up with just the negative cosine function. And that's probably the best way to do this one because I can just visually see it as a negative cosine function. In fact, just kind of for fun, I'm going to put in a plus pi and do my little trig identity because it says cosine of the first times cosine of the second minus sine of the first times sine of the second. And if I do that, I will see that this term is a 0 because sine of pi is 0. And this one, cosine of pi, is a negative 1. And so we get negative a cosine omega t. And that would be the mathematical proof showing you how this function here is the same as that function. You can also see then why the plus or minus pi would work up here. So minus plus, because cosine of either a plus pi or a minus pi is still a negative 1. But again, I think, especially being a physics class, we should really not focus too much on our mathematics, although we need a lot of mathematics, but we should focus on the physical picture, and it would make the physical picture saying, look, I'm starting with a negative value and it oscillates back and forth, so I know it is a negative cosine function. And in this case, since we pull it 3 centimeters, and I'll write that as 0.03 meters, then we have our amplitude, and the omega, which I guess I haven't calculated, I've mentioned it, but the spring constant was the 25, and the mass is 1. Oh, and then the square root makes a nice even 5. So this is 5t. And so there would be the mathematical equation for, what is the position of it. Now, I don't know if I need that or not, but let's go on to the first question. Find A, the period of motion. All right, so the period of motion is 2 pi divided by omega. Omega, as we said, is this 5, the square root k over m, and so this is going to be 2 pi over 5. And so 2 pi divided by 5 is about a 1.26 seconds to go back and forth for the period of oscillation. So there's A. B, the maximum value of the speed and acceleration. Well, in our derivation, we got maximum by taking the derivative of this and looking at the function. In fact, maybe I'll take the derivative. So the derivative of position gives me velocity. And then when I take this derivative of a cosine is a minus sign. And so this cosine is going to be converted into a sine. And I should say minus sign, so that the 2 minuses go away. That's why it's a positive. The chain rule is going to pull out an omega, and of course the A is just some kind of constant. But this equation says that we've got something out in front times a function that goes up, down, up, down, up, down, up, down, and the biggest it ever gets is 1. So this omega A, as we wrote here, must be the maximum velocity. And so we have our omega, which is 5 radians per second. And we have our amplitude, which is 0.05 meters. And radians per second. Together make a 3 times 5 is 15, 2 decimal places, and then meter per second. So its max speed is 0.15 seconds. Nice. Now, acceleration comes out to be omega squared A for its maximum. Now, to prove that again, I'll just take the derivative one more time. So the derivative of velocity is acceleration, and derivative of a sine function is a cosine and a plus cosine, so this is still a plus. We have the omega A from here, but the chain rule gives me another omega. And if we read this, we'll see that you have something out in front of another trig function that goes up, down, up, down, up, down, up, down. And the largest it ever gets is 1, so the largest this would ever get or the whole thing would ever get, would be this number times that 1. And so that's why we said it would be omega squared A. And so this would be 25 times 3, which is 75. And then 2 decimal places. And the units here would be meters, and over here would be seconds squared. And so 0.75 seconds squared is the total of that product. Okay, good. Let me keep going. I guess I haven't used my yellow sheet here. Kind of fit it on the white sheet, but I'll go on to C. The position, velocity, and acceleration as functions of time. Oh, so I didn't read it, but I actually solved those. Here is the equation as a function of time, position. Here is the velocity. Maybe I put some numbers in. And here is the acceleration. So to finish it up, I'll say, okay, so position would be a negative 0.03 cosine 5t. Velocity would be this maximum that we did here. So that would be 0.15 meters per second, and meters here. And then this would be sine omega t. So that would be that one when you put the numbers in. And the acceleration would be this maximum value. And omega a was, what was that value? Oh, there it is, 0.75 meters per second squared. And then cosine omega t, which is the 5t. And so that would be the best way, putting in everything I do know and then just having nothing but time left as the variable, because it says as a function of time. And so all of these are saying, you give me the time, I can give you any of those. Or the other way around, you give me any of those, I can give you the time. In fact, just give me one of these equations and I can give you all of that. That's kind of the whole lesson of it. Okay, good. There is example number 2 I wanted to do. Okay. The next one on my list was number 16. So let's give that one a little try here. And again, I printed it up. So here it says a block spring system oscillating with an amplitude of 3.5 centimeters. A spring constant is 250 newtons per meter. And the mass of the block is 0.5 kilogram. Determine A, the mechanical energy. Okay, here's some fun things we haven't done for a while. And so the mechanical energy is made up of kinetic energy and potential energy. And in this case would be 1/2 mv squared and 1/2 kx squared. And since it's a constant, you could apply this anywhere you want. And so if something, starts here and oscillates back and forth, if you apply this equation when it is at one of the extremes, then you would have no velocity and your position would be the amplitude. Now, on the other hand, if you applied this equation when it's in the middle, it would have 0 position and would all be its maximum speed at its, midpoint there. And so this is another way to get the total energy. So it's kind of one and the same, but we could say, well, one way of getting it is by just knowing its amplitude. Another way of getting it is just knowing its maximum speed. Another way would be noting its speed and position. Of course, it would have to be the speed at that position. And we'd have to add those two together. But I think this one is probably best done right here because they directly tell us the spring constant as 250 newtons per meter. And they give us the amplitude, now not in meters, but I'm going to do that in meters, but I have that number, so 0.035 meters squared. And you can see, and now probably you'll see why I wanted to put it in as meters, is because right here, I'm going to get meters squared. And so one of these meters will cancel with one down there, and then I'll be left with a Newton times a meter, which is a joule. So to get this to come out to be joules, I needed to watch my unit. I needed to make sure things were in, newtons for forces and meters for distance, and this amplitude was not, and so it needed to be converted over to meters. In either case, getting a number here, so 1/2 times 250 times 0.035 squared is let's see, 1, 2, 3. Let's call that 3 significant figures, 0.153 joules of energy that's in this system, the mechanical energy of it. And so I would be using this equation. Now for B, when they say the maximum speed, now we can take advantage that we know it's total energy and find its maximum speed. So I'll just put this in as 0.53 joules of energy here, and then a 1/2, and then its mass is a 1/2 kilogram. And that should be equal to the velocity of its maximum, that is when it's at its center, squared. And maybe I'll write it this way, V max, and watch my units here. I'm going to think of this joule as a Newton times a meter. Then I'm going to think of the Newton as a kilogram meter per second squared, so that when I multiply by the meter, I get this total units for a joule. And then, of course, I'm dividing by this 1/2 kilogram. So unit-wise, that'll go away. Then, of course, I'm taking a square root to get velocity maximum by itself. And so that's going to leave me with meters per second. Numerical, that's pretty easy. I've got the energy here. I would bring the 2 over, so times a 2, and then divided by a 0.5, and then a square root. So 0.783 is the maximum speed. V squared times R times 1/2. Let me just double check that. Yeah, and that gives me the same energy. So what is the maximum speed? And then this one, what's the maximum acceleration? I'm tempted to go omega squared A like we did in the first problem. Where did that go? That real long one here, number 4. No, maybe it was the other one. Yeah. Sorry, it was number 10. Number 10, we did, maximum acceleration omega squared A. Of course, I'm not a big fan of that because I don't have the omega, but omega is just the square root of m over k. Square root of k over m. I'm thinking just doing Hooke's law and then Newton's second law might be the way to go, because if we're talking about a maximum here in terms of magnitude, we're going to get that maximum when the position is at its amplitude. So I kind of like that. And oh, actually, this is the same thing as that, because remember, omega is the square root of k over m. And so if you square it, you do get k over m times a, which is also what I got when I went this direction. All right, so, oh, that was good. So maybe you see how they are the one and the same. And of course, we're given these, so this is probably the direction to go here. So my k is 250. My amplitude in meters is 0.035. And my mass in kilograms is 0.1. And so this leaves me with 17.5. And since it's an acceleration, this right here should come out to be newtons, and divided by a kilogram gives me meters per second squared. So there would be the maximum acceleration. And, oh, good. And then that's it for number 16. Nice. All right, let me look back here at the beginning. So we've done 3 so far. Number 4, number 10, number 16. All right, let's go over to number 63. And again, I printed up number 63 to hopefully help with your understanding here. But it says here, and gives us a nice picture, a ball of mass m, so I'll put a little m there, is connected to 2 rubber bands of length L, okay, each, and they're under a tension of T, as shown in the figure. Okay, so they're under some kind of tension. Oh, and I guess we should ask, is it a tension when they're in this position or when it's in that position? Let's keep reading here. The ball is displaced a small distance y, okay, perpendicular to the length of the rubber bands. Okay, so the ball starts here and then we pull it here. So I think they're talking about the tension when it's in this center position, if you will. The ball is displaced a small distance y perpendicular to the length of the rubber bands. Assume that the tension does not change. Okay, so we can say the tension is the same. In reality, it probably changes a little bit from here to here because it looks like we'd be stretching the rubber band a little bit. It kind of depends on how long these lengths are, especially if these aren't drawn to proportion. If this length was really far compared to the vertical displacement here, this would be just kind of minor. That wouldn't change the tension. Okay, so we're told, assume that the tension does not change. Show that A, the restoring force, is equal to this. And then B. So let's do the free body diagram. And let's put it, off of the center line here a little bit. Maybe here. And so the tension on both sides is angled a little bit down. I didn't do a very good drawing here. It should be symmetric. But it needs to be kind of angled down. And if this is some small angle theta, and in our free body diagram, we look at x and y, we would say here that the tension in the x direction from this one is a plus t cosine small angle theta. And this one here is minus t cosine theta. And that's clearly going to be 0. And of course, it has to equal mass times acceleration in the x direction. So acceleration in the x direction is 0. And none of that, I think, is a surprise that as you pull it up here, it's not going to be moving left or right. But it is going to be pulled down, and that's what this column would do. When I go to add up all the forces in the vertical direction and set it equal to MA, the vertical direction would be a t sine theta for this one. And the second one would be identical, so I'll just double it. And that has to equal to mass times acceleration in the y direction. Although I don't think I have to solve this, at least yet, maybe in part B, but I think that's why in A they say the restoring force. So the force that's bringing it back, that would be this whole thing right there, just that piece of it. That is, the x components canceled off completely and went away. They're not restoring anything. And this is the restoring. And so I guess A, the restoring force, would be 2t sine theta. Now, looking at our free body diagram, this theta here, and if you extend the rubber band down to here, would be the same as this theta in the picture here. And sine theta would be opposite over hypotenuse. And so I'm going to replace the sine theta with y over, and I guess technically it's the hypotenuse, but again, they said the length doesn't really change by saying the tension doesn't really change. So this side here is pretty close to L over L. And I think that's what they want. Although I just noticed here, I should have been a little careful. This force is pulling downward when the ball goes up, or not shown in the picture, but if I pulled the ball down, the force would be up. So the restoring force is really a negative of that. So this should have been a negative and a negative. And so I think we have what they're asking for. And that is show that the restoring force has a negative, so negative 2t over L, and then a y. Yay! Okay. Because, again, going along this equation, I'm calling this a negative 2ty over L minus ma, and a is the second derivative of position with respect to time. And rewriting this as minus 2t over ml, when I bring the m over here, and bringing the y off by itself, we have that magical equation I keep warning you about. That anytime you see something that, that's the same function, and you take its second derivative, you end up with that same function, you end up with a minus sign and something out in front. This stuff out in front is omega squared. And so this right here with our free body diagram and this equation for the y motion, not the x, but for the y motion, would tell us right away what omega is. And so omega should be the square root of 2t over ml. And I think that's what the problem says. It says the system exhibits simple harmonic motion. Yep, that's what an equation. It says anytime we have an equation like that, it's going to be sines and cosines, simple harmonic motion. And it says with an angular frequency omega equaling, yep, and sure enough, that's what we got. All right, good. There's our fourth example. And the last one is number 58. And this will make the 5 examples that I kind of wanted to really do in class, but just ran out of time and thought I'd go ahead and put this together. Maybe it will be useful for somebody as you struggle along here with the problems. So 58, and it says review problem. So there's probably something from the first 14 chapters in here, like moment of inertia or conservation of energy, linear momentum, angular momentum. Oh, I see here that they're going to be hooked together and dropped together. So I think that's why review problem. There's going to be some conservation of momentum popping up here. But let's read it together here. A particle of mass 4 kilograms is attached to a spring with a spring constant of 100 newtons per meter, and it oscillates on a horizontal frictionless surface with an amplitude of 2 meters. Okay, so I guess here's what I have. Got this 4 kilogram object attached to a spring constant 100. It oscillates back and forth. That means somebody pulled it or bumped it and it started swinging. We also know that the angular frequency is the square root of k over m. So k is 100, m is 4. That was nice. They gave me the square root of 25, which is just 5. So this is going to be my angular frequency of 5, and it would be 5 radians per second if we want to watch here our unit. But let's see. It oscillates on a horizontal frictionless surface with an amplitude of 2. So maybe I'll put 2 meters for the amplitude. Then another object, a 6 kilogram object, is dropped vertically on top of the point 4 as it passes through equilibrium and the two objects stick together. And so here is where we can say initial momentum is equal to final momentum, at least in the x direction. Because the picture I have here is, okay, I've got this 4 kilogram object. And as it goes back and forth, and let's just say at this particular moment it's heading towards the right, we then come along and drop a 6 kilogram object on top of it. And that impact and that drop would be in a vertical direction, and so there would be a lot of forces and normal force here from the tabletop that would, say that momentum in the y direction is not conserved. But it doesn't do any effect on the momentum in the x direction. Now, once this block of 6 kilograms lands on top of the 4, there's going to be, rubbing going on. And so the block of 4 is going to drag it along, and eventually they're going to be together. But this interaction that makes, I guess I'd say, the 6 kilogram go faster and the 4 kilogram go slower, if we think of them as a system, that's an internal force. And so momentum in the x direction is conserved. So I think that's what they are after this with calling it a review problem, that we actually have a collision where momentum is then conserved in the x direction, but not in the y direction. And so with that in mind, I would usually write something like this. The initial momentum in the x direction is equal to final momentum in the x direction. And before they collide, we have a 4 kilogram object traveling with some speed, let me call it V max when it gets to equilibrium, then runs into, or actually the other one is dropped on top of it. So you could then say the two together, once they start moving together. So like I said, there's going to be a little bit of rubbing going on. So you drop the 6 and then there's some rubbing. So the 6, falls down, and then there's some rubbing. And so it's going to continue to go back and forth. So I guess it looks kind of like this. The 4 comes in, the 6 goes out, slides, builds up speed, and then it keeps rocking. But once it's rocking, it's stuck together. And this is what we call a perfect inelastic collision. And so I'm going to think of it as one big object of 10 kilograms, and then they would have some new speed. You can see that the speed is changing as this rubbing goes on. The 4 is slowing down, and then the 6 is then speeding up. I haven't calculated yet what that 4 would be, but like we did in the previous problem, we know in terms of energy, this is the total energy, and so is this. So, squared. So we could take the information given, which is 1/2, spring constant of 100, amplitude of 2 squared, and say that must equal to 1/2 times its mass of 4 and its maximum speed. Now notice I put a 4 here, and what I meant by that is this is before the collision, so maybe I should draw a line here. So this was kind of my thinking that, hey, we're going to have a collision. We're going to go from an object that has 4 up to an object that has now 10. But before that collision, in order to calculate what its maximum speed is right before the impact of this 6 kilogram mass falling on it, I would say this is, how I get the maximum speed. And it looks like the 1/2 cancel off. This 2 squared is actually then a 4. And then when I take the square root, we're looking at 10. So we know then that the speed before the collision is going to be a speed of 10. So that's what I could use back here. So this 4 times a speed of 10 now has to equal 10 times its new speed, which makes the math kind of easy. The new speed is going to be down to 4 meters per second. All right, so in the picture, as this thing's rocking back and forth, it goes back, it gets going, and right here, right before the impact, it's moving at a pretty good speed of 10 meters per second. Then we drop this on it, and they rub and stick together, and now they're just heading off with a measly speed of 4. Of course, it's heavier also. But the energy has dropped some because, I should say mechanical energy, there's going to be rubbing and friction there. Now, I haven't quite answered that first question, which says, by how much does the amplitude of the vibrating system change as a result of this collision? So let me apply this same equation, but now doing it after the collision. So we have 1/2 K, and we have what you call maybe a new amplitude, equals 1/2 times its new mass, traveling at its new maximum speed. Now, of course, the spring is still 100. And so these two together are a 50 times this new angular momentum. Let's see, what is this number? This would be 80, is that right? I think that would be right, because 16 times 10, 160, and then half of that is 80, yeah. All right, so if I take the 80 and divide it by the 50, and then take its square root, we're looking at 1.26 meters for the new amplitude after this collision. So hopefully you do see that it's a review problem, but also it is a problem involving the energies of oscillation. We're going to do that twice. Once when it was oscillating before the extra mass was added, and then once afterwards. I guess technically I didn't answer the question, which is the change in it. And so we'd have to go 2 minus 0.126, because this is the new amplitude. So the change in amplitude is 0.735, we'll call it. That's how much amplitude we lost by giving it more mass and then also making it rub. All right, well, that was a good one by itself, but there's more to this problem. Let's see. B, by how much does the period change? Okay, so the period before, I'll go B4, and the period after are listed here. So the period before, which would be 2 pi over omega, and omega would be the square root of k over m, and so since it's in the bottom, I'll flip it to the top. And so this would be 2 pi times a mass of 4 and a spring constant of 100. So 4 divided by 100 is 1/25, 0.04. I'll take the square root of that, which must be 0.2. And then times a2 times a pi. And, oh, and I think we did this one, 1.26. Maybe that was another problem. I don't know if I did the period on this one yet. Okay. Now, after they collide, so 2 pi, again, over omega, and omega is k over m, so let's be m over k, is going to be 2 pi, and now we have a mass of 10, and we still have a spring constant of 100. So this would be 10 divided by 100, which is a tenth, and we can then take the square root of that and multiply that by a 2 and a pi, and we now get a period of 1.99 seconds, which again, it's got more mass. It's got a smaller amplitude too, but the period never really depended on the amplitude. That was kind of one of the steps. I guess it was step 4 in the lab, where you had to prove by experiment until you measured the period of different pendulums with different amplitudes, and you show that, well, that doesn't matter. So the period does change, but because of the mass change, not because of the amplitude change, which is also a loss of energy. How much does its energy change? And I think the author really means mechanical energy here, because if I go, I'll go 1/2 k a squared for the before picture and 1/2 k a squared for the after picture. And both of them have a spring constant of 100, both before and after. We didn't really change any of that. But as we talked about, the amplitude before the collision was a 4, and then we squared it. I mean, a 2, and that was given, and then we squared it. Then as we were calculating the energies, we said that, okay, we got to conserve momentum, and so there's going to be a new amplitude. And so this new amplitude is 1.26 meters. All right, so let's see, 400, half of that is 200. So this is 200 joules. This one's not so easy, 1.26 squared times, I'll just call that a 50, And so this is 79, I'll call it 0.4 joules. So this collision, this impact, we lost more than half of the mechanical energy. The difference between them must be the rubbing and the heat that got created. And so I think that's what they want to say here. How much does the energy change by? And then D, account for this change. Well, that's what we just did. There was a change, and the change must have decreased because as as this one was going back and forth, this one was coming, this one was falling, hit it, rubbed, and so now they have a lower than the 200, which apparently went down from 200 to about 80. And that means 120 of it went somewhere else because of conservation of energy, and that's the rubbing and that's the heat. So that's why I wanted to interpret the part C as the change of mechanical energy, because there wouldn't be any change in total energy. But we did lose 120 joules of mechanical energy. It showed up then as heat and the rubbing of the two. So almost, well, it is 120 out of 200. Is that, yeah, 60%. So 60% of this energy, sadly, is now gone because of the collision. This would be a pretty good size collision anyways. And that's where it all went. Okay, and I think that's it. All right, so there's my 3 examples. Hopefully that was helpful, and take care, everybody.